Good morning. This video covers periodic trends. A trend is a generalization that uses patterns to explain some type of phenomena. We will use the trends to predict characteristic properties of the elements based on the number of valence electrons. This video will cover atomic radius and ionic radius, ionization energy, electron affinity, electronegativity, and metallic character. Each trend has a group and a period trend. The period trend is the trend that occurs in elements across a row on the periodic table, horizontally, and the group trend is the trend that occurs within a family as you go down a column on the periodic table. You will learn how to evaluate the trends looking at the periodic table, but that is not enough. You need to be able to explain why a trend occurs the way it does. To do so, there are four main explanations that you will want to focus on. The first of them is called the effective nuclear charge. It is commonly referred to as Z effective, and it is the average shielding charge felt by an electron. When we look at the Z effective, you can figure it out by taking the Z, or if you remember the atomic number, minus the number of the inner shell or core electrons. If we think about a Bohr model for something like sodium, just very simply, I would have 2 electrons in the first shell, I'd have 8 electrons in the second shell, and I'd have 1 electron in the outermost shell. So this is my valence electron, and the 10 electrons that are found in the first and second energy levels, those are the core electrons. So when we look at this, the Z effective basically looks at the atomic number, which would be 11, subtracting off the number of core electrons, that would be 10, giving us a Z effective of 1. The Z effective is only to be utilized for period trends. And the reason for that is the fact that as we look at one of the next elements, if we do aluminum, for instance, I'd have 2 electrons, 8 electrons, and then 3 electrons. So my number of core electrons stays the same, although I've increased my number of protons from 11 to 13, but I've now increased the outer shell from 1 to 3 as well. And so the 10 electrons in the middle staying the same will provide the same amount of shielding from the nucleus. And so the core electrons will not change. If we look at a group trend, although the number of protons is changing in the nucleus, the number of the core electrons is also changing proportionally, and as a result, we'll have the same Z effective for the group trend. The second of our explanations is the shielding effect. So when we talk about the shielding effect, we're talking about shielding in an atom as the blocking or the canceling of positive charge by those core electrons. So this is what I was referencing. As we increase the number of core electrons that are inside, it is going to provide a larger degree of blocking from the outer shell, and as a result, that increase in distance will reduce the force of attraction. So in this case, it's going to reduce the force of attraction. I'm going to abbreviate force of attraction as FOA for our purposes. So this reduces the force of attraction that's occurring between the nucleus and the outer shell. So we only want to use the shielding for a group trend. Our next explanation is Coulomb's law, or commonly referred to as the law of inverse squares. Coulomb's law shows that the force of attraction between two oppositely charged particles is directly proportional to the magnitude of the charges, meaning that if I have a +2 and a -2 versus a +1 and a -1, and inversely proportional to the distance between those two charges. This can also work for forces of repulsion if you have, say, the 2 electrons as your charged particles. But as you increase the amount of charge, it's directly proportional, so you'll get a larger number in the numerator. As you decrease the distance, you get a smaller number in the denominator, which would increase that force of attraction. This can be used for either group or period trends. And then our last one is minimizing electron-electron repulsions. So this is going to put the atom at a lower energy state and is going to make it more stable. Please remember to relate everything to energy as much as possible. All the atoms, again, want to be as low in energy as possible to gain a greater amount of stability. The first of our trends will be atomic radii. Please remember that for the atom, it is mostly made up of empty space and therefore has no definitive boundary of where one atom ends and the next atom begins. As a result, we define the atomic radius for an element as half the distance between the nuclei of a diatomic molecule of the element. We might expect that the atomic radius would increase as we move from left to right across the periodic table. However, if you look at the chart on the left side, you can see that you actually have the atomic radius getting smaller as we go across. Why would that occur? The answer is because of the increase in the effective nuclear charge. Please remember that the effective nuclear charge is looking at the overall attractive force that's coming from the nucleus on the outer shell electrons. It is affected by the number of core electrons that are in the way. When we look at the diagram to the left, you'll see that I picked two elements from the second period, lithium and fluorine. Lithium has 3 protons while fluorine has 9. You'll notice that both of the atoms only contain 2 core electrons, but lithium has only 1 valence electron where fluorine has 7 valence electrons. This increase in the opposite charges will cause a stronger force of attraction to occur between the nucleus and the outer shell, and therefore will draw in the electrons closer to the nucleus. So just as a general rule of thumb, as the Z effective will increase as we go across the period from left to right, it is going to have a stronger force of attraction, which will cause the radius to be smaller. As we look at the group trend, your general trend will be that the atomic radius is going to increase as we go down a group. If you remember from our atomic theory unit, we talked about the different quantum numbers, and the principal quantum number n will increase as we go down a group because that is talking about how many different energy levels are filled with electrons. So I took sodium, which is directly below lithium in group 1, and you'll notice that for sodium I've added 8 protons into the nucleus, and I've also added 8 more core electrons. So that's why when we look at the Z effective, we don't want to use this argument for the group trend. I have the same ratio of the core electrons to the protons. I have 11 and 10 versus 3 and 2, so I have an effective nuclear charge of 1 for both lithium and sodium. However, I have increased the distance from the outer shell to the nucleus, and so as a result, the force of attraction, Coulomb's law, is going to be a smaller amount, and the shielding is going to increase because of the extra 8 electrons in the core, and as a result of that, you're going to have a weaker force of attraction overall between the nucleus and the outer shell. So again, sodium now has 10 core electrons instead of 2. Even though I've added 8 protons, that force of attraction is going to be weakened as it goes down. So when you guys are looking at your periodic tables, you have a couple of general trends. I'm always going to be doing my drawings here showing an increase in the direction on the periodic table. So for your atomic radius, which I'm just going to abbreviate as AR, it is going to increase as we go from right to left, and then from top to bottom across your periodic table. So now let's look at how we can utilize this to compare different elements to each other. Okay, so in our first example, we are going to look at the periodic table, and we're going to rank each set of main group elements in terms of decreasing atomic size. So we want to go from the largest to the smallest. So again, the general trend that we had for increasing was going from right to left and from top to bottom. So as I look at the first one, calcium, magnesium, and strontium, you'll notice that these elements are all found in the same group. So I want to focus on the group trend to evaluate this. So since my size is going to increase as we go down the group, if we want decreasing size, we want to start with the largest. So strontium would have the greatest number of energy levels filled with electrons. So I would have strontium first. and then I would have calcium, and I'm going to go ahead and put the sizes on as a greater than. The strontium would be greater than calcium, which is in the middle, and then magnesium would represent the smallest of my different ions. When I look at my second set, I now have potassium, calcium, and gallium as my three choices. So when I look at my periodic table, again, it increases across a period going from right to left. So gallium would represent my smallest, potassium would be my largest because it's the furthest to the left. So I'd have potassium, and then I would have calcium, and finally I would have gallium. So again, for this one, increase in the effective nuclear charge as I go across. They all have 18 core electrons, but again, I have an increase in the protons in the nucleus and the number of valence electrons in the outer shell, and that's going to cause the radius to shrink. My next example, Br, Rb, and Kr. So let me go ahead and erase those really quickly here. So if I'm looking at this, I have bromine, krypton, and rubidium. So you'll notice this is the first instance where we have elements that are found in different energy levels for the periodic table. So to evaluate first between my krypton and bromine, they're right next to each other. Again, the krypton being further to the right on the periodic table has one more proton and one more electron. Both have 18 core electrons, so I'm going to have a stronger force of attraction with krypton, which is going to make it smaller than bromine. With rubidium being in the 5th energy level, it now has 36 core electrons and only one valence electron. So having that extra energy level going to provide extra shielding, larger distance from the nucleus, so rubidium would be my largest. And now bromine, because it has that one less electron, it will be the second largest, and then krypton will be my smallest. So we have that for C. And now if we look at strontium, calcium, and rubidium, again, I have different elements that are not found in the same period or in the same group, but we can use the same basic principles to help us figure this out. So I know for my group trend, as I go down, it's increasing, so I know that strontium has to be larger than calcium. So as a result, I'm going to have strontium here being greater than calcium. And now to decide where to put rubidium, notice that rubidium again is in period 5 versus calcium in period 4. So having that one extra set of energy levels, I know that the rubidium will be larger than calcium, but now between strontium and rubidium, I know that the rubidium being further to the left, having one less proton, one less electron in the outer shell, will have a weaker force of attraction. So as a result, it will be the larger of those two elements. Next, we're going to look at ionic radii. For the ionic radii, we have two different types of ions. We have cations, which if you remember are losing electrons, and we have anions where they are gaining electrons. The trend is going to be different depending on whether it is a cation or an anion. So let's first look at cations. In the diagram to the left, you'll notice that I have a Bohr model for the sodium atom and for the sodium ion. When the sodium atom loses an electron, it is going to lose its 3s1 electron, so it's going from having 3 energy levels filled with electrons to now just 2 energy levels filled with electrons. And so as a result, the number of core electrons is going to drop from 10 down to 2, which means that with 11 protons still in the nucleus, we're going to have a stronger force of attraction. That increase in the force of attraction will cause the atom size to decrease. When we look at the anions, now we're not adding in extra energy levels when we fill the electrons into the outer shell. However, what we're doing is we are increasing the amount of repulsion between the electrons. And that extra repulsion is going to cause the outside electrons to expand in their size. So when we talk about the cation versus the parent, it's going to get smaller. When we talk about the anion versus the parent, they're always going to be larger. For the trends when we're comparing different ions to each other, the ionic radius is going to increase still while we go down a group, because even though I'm still losing electrons, I am adding extra energy levels filled with the electrons. And so we would expect the potassium ion, with having 3 energy levels filled with electrons, to be larger than the sodium ion having only 2 energy levels filled with electrons. So when we look at the period trend, the cation size will decrease as the charge will increase. Again, the same concept. I have the same number of protons in the nucleus, but I'm reducing the number of energy levels filled with electrons. That increase in the effective nuclear charge is going to cause a greater decrease in size. If we have an isoelectronic series, which if you remember means that they have the same number of electrons, basically have the same electron configuration, but they have the different number of protons in the nucleus. When we look at that, the greater the size for the cation is going to cause a smaller atom, and on the anion side, having the extra electrons added in is going to increase the amount of repulsion each time. So having an increase in charge for the anion is going to cause a greater increase in size. So the ion that's -3 will be larger than the ion that's -2, larger than the ion that's -1, and then you have that being larger than a +1, which is larger than +2, and larger than +3. I just wanted to take a moment and graphically show you guys this last concept with the isoelectronic series. Each one of these would have an electron configuration that would be 1s2, 2s2, 2p6, therefore having 10 total electrons. Again, the size difference is going to be based off of the number of protons. The greater the number of protons, the stronger that force of attraction will be between the nucleus and the outer shell, Coulomb's law, and so the size of the atom will shrink, or the size of the ion will shrink. So if you notice here, nitrogen having 7 protons, 3 minus charge, it has the largest ionic radius of 146. Oxygen, the oxide ion, now having 8 protons versus the 10 electrons, it shrinks down a little bit to 140, and then fluorine going to 133 when it forms the fluoride ion, still having 9 protons. When I go on the cation side for this, having the 10 electrons, sodium losing 1, magnesium 2, aluminum 3, I go from having an ionic radius of 102 for the sodium all the way down to 54 for the aluminum ion. So again, basic rule of thumb for you, as the number of protons increases for those isoelectronic series, the radius will decrease.